In chapter 6, we were discussing thermochemistry. And thermochemistry has to do with the amount of heat that is released when a reaction happens. And as an example of this, what mass of liquid octane, component of gasoline, must be burned in order to provide 6.05 times 10 to the fourth kilojoules of heat. And then we have delta H equals minus 5471 kilojoules per mole of C8H18 that is burned. So we need a balanced chemical equation here, and this balances the equation. And then we add the energy term. This delta H, you should notice this number that I have here is double what this number is. This is the energy that we have given up here in the problem. This is the energy that's released per mole of C8H18. In this balanced chemical equation, however, to have it properly balanced, we have to have 2 moles of C8H18. And so I've doubled the amount of energy that's released for that process, since I'm now dealing with 2 moles rather than 1. Okay, and now we can get down to the business of what mass of this liquid octane needs to be burned to provide that amount of energy. So here's the amount of energy I've written down. Now we can use the balanced chemical equation that tells us for 2 moles of C8H18, we're releasing 10,942 kilojoules of heat. Those cancel each other. And now, since we've asked for a mass, we use the molar mass for C8H18, which we've calculated from the periodic table. And that tells us that 1,263 grams of octane. When that is combusted, we get out 6.05 times 10 to the 4 kilojoules of heat. We talked quite a bit more about this heat equation, and we'll use that now. How much energy must be transferred to raise the temperature of a cup of water, 250 mLs, from 20.5 to 95.6 degrees C. And here we're given the specific heat for the water. And in these cases, we'll use this equation. So Q, which is heat, and this has units of joules, is equal to the mass of the whatever substance we're talking about, times the S value for that substance, times the change in temperature. And so here's all the pieces that we need. We have, this is, actually they're switched, so this is the S value that's put in right here. Right here is the mass, and we've made the assumption that the density of water is 1, and so 250 mLs of water is equal to 250 grams of water. And then finally we put in the temperature change here. And this is another typo in this one. This should be degrees C. So the change in degrees C here, and once I put all these pieces in, I get 78554 joules of energy. Okay, and this positive value means that energy was transferred to the water as heat. It is a positive value because the water is being heated up. So it's going from 20.5 degrees C up to 95.6 degrees C. And the process of heating the water up requires the input of energy. We also talked about this type of process where we have a hot piece of metal and we put it into a container containing cooled water. And then what happens is the hot metal transfers to the heat to the cold water. And as this process goes on, what eventually happens is the water ends up slightly warmer and the metal ends up much, much cooler than it started. And if you look at the precise numbers, right, we go from 21.0 up to 23, so we increased just a little over 2 degrees C. The water did, but the metal went all the way down from 99.8 degrees C all the way down to 23 degrees C. And this is what will always happen. Heat will transfer from a hot object to a cool object until they're the same temperature. Once they're the same temperature, neither has any additional heat energy in it, and so the transfer stops the moment that they're both the same temperature. All right, here's some things to think about. The metal and the water are the system. The beaker and the lab are the surroundings. The metal and the water always end up at the same temperature once the process is complete. We'll assume that energy is transferred only as heat, so we're not losing it as light or something like that. We'll assume that all of the water from the, or all of the heat from the metal ends up in the water. We're not losing any to the environment. This is probably the most important part here. We need a negative sign on one side or the other, because the heat that, for example, here is leaving the metal goes into the water, but it has a different sign when it does, because one of them is going down in temperature and one of them is going up in temperature. And so we end up with two equations, and we're going to set these equal to each other and make sure to put a negative sign in there. Okay, when we do all of that, this is what we're finally going for. So a negative, and the negative can be on either side. It just needs to be on one side or the other. So a negative times the mass of the metal times the specific heat of the metal times the change in the temperature of the metal is equal to the mass of the water times the specific heat of the water times the change in the temperature of the water. Okay, and so here's the type of problem then that you guys would see for this. So you're given a mass of a piece of iron, and you're given its initial temperature, and it is placed in a beaker with some mass of water and the initial temperature of the water. You're given the specific heat for the metal and the specific heat for the water, and then asked to figure out what the final temperature is. And so this is the things we talked about before. And so then finally, I've just went here and I've pulled all the data down into the equations. And then to go from this step to this, I've just taken my calculator. I've multiplied 244 times 4.184 times TF, and that gives me the first term. 244 times 4.184 times minus 18. I cannot lose this minus, or it screws me up. And I get this minus 18376. And the second term here, 88.5 times 0.444 times TF becomes this term. And then my last term is 88.5 times 0.444 times minus 79 becomes this term. Do a little bit of rearranging, put the TFs together and put the other part that doesn't have a TF together, divide both sides by the 760, and I'm left with the final temperature here being 20 degrees C. That fits with the things that we've seen before. So the water has heated up from 18 to 20. The metal has cooled down from 79 to 20. All right, another important thing from this chapter is Hess's law. Delta H for a process is the sum of the delta H of the individual steps. And so if we can figure out a way with steps to do the overall process, then we've figured out a way to calculate the energy. And so, for example, we might be interested in taking a carbon atom and combining it with half of an O2, so a carbon atom with an oxygen atom to give us carbon monoxide. And then on our paper, we would be given two equations, and we would need to do something to manipulate these so that these equations would add together at the end to give us the equation that we're interested in. And I always suggest first we want to make sure that everything is on the correct side. And so it looks to be, so CO is a product, and then in this first given equation, CO is a product, so that looks good. Carbon is a reactant, and carbon is a reactant. So as far as that goes, we're good. And I think over everything else, we should be good to go. Let's see. So carbon, we have one O2, and then we have half of an O2. So a half O2 will cancel half of this whole O2, and then the CO2s will cancel. So yeah, we're in good shape. So cancel, and then yeah, this half cancels that. So our net reaction works out. So once we've canceled everything, we need what we're left with to be what we're looking for. And then if that works, now I just need to do the same thing to the numbers. So I take the plus 283 and add it to a minus 393. And I get minus 110 kilojoules per mole. Okay, let's do one where we have to do a little bit more work. So for this one, we take carbon and we want to add 2 hydrogens to make CH4. We're given now 3 reactions. And again, we want to make sure everything's on the side that it's going to need to be on. So carbon is a reactant, and carbon only shows up right here as a reactant. That's good. Hydrogen here is a reactant, and we need it to be a reactant, so that's good. Oh, we run into a problem with this one though. CH4 is a reactant. We need it to be a product, and so we're going to have to flip that last one. Okay, the first one, we're in good shape in every way. We need 1 mole of carbon. We have 1 mole of carbon. The second one, well, hydrogen's on the right side is a reactant, and we need it to be a reactant, but there's not enough of it. So I double everything. So 2 H2s, 1 O2, 2 H2Os, and that means I also need to double the energy. And then, yeah, this last one, we decided it was on the wrong side. So we take and we flip everything. We make the reactants into products and the products into reactants. And that's the only thing we need to do to fix it. And so we flip it over, and after we flip it, we change the sign. So this was minus 980, minus 890. It becomes plus 890. And now, if we go through, everything cancels as it should. CO2 cancels CO2. O2 and O2 cancels 2O2, 2H2O and 2H2O cancel, and we're left with carbon, 2 H2s, and a CH4, which is exactly what we were looking for. And now we're just going to combine the values in the same way. So I'm going to add these 3 values together, and for this entire process I get minus 75 kilojoules per mole.